morning guys, welcome to today's worked exam answer video. Today I'm having a look at a buffer question which has come from quite an old AQA paper but still very relevant, and it would also be relevant to those of you studying the AQA A specification as well. So we've got two parts to this with different buffer systems. They mention the one that's in the body, in the blood, involving the hydrogen carbonate ion and carbonic acid. And then we go on to have a think about dyes in industry, and in this case we're using ethanoic acid with sodium ethanoate. And I guess these are still kind of questions that you would get. The difference, I think, being particularly in part B, they've broken it down into sort of part I, and III, whereas nowadays it would just be calculate the pH of the solution, and it wouldn't give you these sort of hints. As a result of that, whilst I probably would do it in this order anyway, I'm just going to show you how I would do it to work out the final solution pH. Okay, so in the human body, one important buffer system in blood involves hydrogen carbonate ions and carbonic acid, which is formed when carbon dioxide dissolves in water. Also, I have absolutely no idea why it's printed all weird with the subscripts and superscripts, so please ignore that. First of all, it says use the following equation to explain how this buffer maintains a constant pH of 7.41 even if a small amount of acid enters the bloodstream. So when we're thinking about any buffer solution, by definition, a buffer solution is one that is able to maintain its pH upon addition of small amounts of acid, base, or water. And that is because of this equilibrium that we have here. Now, if a small amount of acid enters the bloodstream, that is going to increase the amount of H+ ions that we have in the buffer solution. And according to Le Chatelier, he said that the system will always act to oppose or counteract the change. So if more acid enters the bloodstream, the HCO3- ions will react with the extra H+ to get rid of it, to bring the H+ concentration back down to what it was before. And the position of equilibrium will therefore shift towards the left-hand side, towards the carbonic acid. Now that means that we are going to lose some of the HCO3- because that is what is reacting with those H+ ions. So we are going to lose some of that, but we are then going to make more H2CO3. And this is exactly what we're going to be doing in part B of this question, is working out exactly how much acid has been added, exactly how much of the HCO3- ions in this case have been lost, and how much extra H2CO3 in this case has been made. And I've shown it here to demonstrate the point of how the buffer solution kind of works, but fundamentally any buffer will maintain its pH because the ratio of acid to salt is going to remain pretty much constant, if not completely constant. And that again comes from when we write our Ka expression and then we rearrange it to get H+, which I'll do. So Ka would be equal to the concentration of H+ ions times the concentration of HCO3- ions divided by the concentration of the H2CO3. And then in terms of rearranging it to get H+ equals, we want to do that because that's how we're going to be able to get pH. So H+ would be equal to the value for Ka times concentration of H2CO3, which is the weak acid, divided by the salt of the weak acid, HCO3 minus. So if the ratio of these two things is staying approximately constant and Ka is a constant, then H plus is going to be kept pretty much constant, and therefore the pH is going to be kept nigh on constant. The H plus concentration will change, but because the pH is a logarithmic scale of the H plus concentration, the change in pH is less noticeable. So the pH won't necessarily stay exactly 7.41. It will potentially change to sort of like 7.39 or 7.43, but that would be classed as the pH staying constant. So the answer that you always want to give for this is that whatever weak acid you have, obviously be specific to the question, is always going to be in the same ratio as the salt of the weak acid. So that ratio remains almost constant. And as I said, that therefore means that the H plus concentration will stay pretty much constant, and therefore the pH will stay pretty much constant. Now going on to the calculation for this part, it's asking us to calculate the Ka value for carbonic acid. So they've given us the concentrations of the salt ions, the HCO3 minus ions. So the concentration of those is 2.5 times 10 to the minus 2. The concentration of the carbonic acid, the weak acid, is also given. And then from the pH, we will be able to get the H plus concentration. And in this case, we are attempting to work out the Ka value. So having already written the Ka expression is very useful. Usually, and what we'll be doing in the latter part of this question is then rearranging the Ka expression. You don't so much get questions like this anymore, but hey, it's still something that they could, in theory, ask you to do. So, first of all, how do we get the H plus concentration? We do that by doing 10 to the power of minus pH, and that's like the inverse of doing minus log 10 of the H plus concentration. And handily on my calculator, my log button is here, and my 10 to the power of button is on the same button. I just need to shift and then press that. So minus pH is 7.41. So that is my H plus concentration. .89 times 10 to the power of minus 8. And that's then everything that I need to be able to work out Ka. So Ka will be equal to, I'm going to use this version here, so the H plus concentration is what we've just calculated. And then that is times by the salt of the weak acid concentration. So that's going to be 2.50 times 10 to the minus 2. And then we're going to divide that by the weak acid concentration, which is 1.25 times 10 to the minus 3. And that will get us our value for Ka, which is the acid dissociation constant, which is going to give us an idea of how strong or weak of a weak acid carbonic acid is, because we know that all weak acids only slightly dissociate. So the Ka value essentially tells us how much dissociation there is. The bigger the Ka value, the stronger the acid. So the fact that this is 7.78 times 10 to the minus 7, that is quite small. And so that is quite a weak acid. So it turns out. That's all we need to do for that one. Now we're going to be using, like I say, really similar things in part B. So it says, in industry, the pH of a solution used to dye cloth must be controlled or else the colour will vary. Makes sense. A solution of dye in a beaker is buffered by the presence of ethanoic acid, which is our weak acid, and sodium ethanoate, which is the salt of the weak acid. It says in the solution, the concentration of the ethanoic acid is 0.15 mole per decimetre cubed. Concentration of sodium ethanoate is 0.1 mole per decimetre cubed. And then here's a nice comparison. The value of Ka for ethanoic acid is 1.74 times 10 to the minus 5. So definitely stronger than carbonic acid. Now, as I said, this part has been broken up into 3. So we're going to be adding acid to the buffer, and it's given us a volume of acid that we're adding, and it's given us a concentration of the acid that we are adding, and then it's telling us that we're adding it to 1,000 centimetres cubed. And that is helpful to know, because when we are working out kind of what goes on with our equilibrium, we need to consider it in terms of how many moles of the salt and moles of the weak acid are going to be lost and made, and then work out what the new moles will be. So by knowing that the volume is 1 decimetre cubed, the concentrations are essentially the moles, which is helpful. So the first thing that I would be doing is calculating the moles of hydrochloric acid so that I can deduce what's going to go on with my equilibrium, which you'll see in a second. Calculate the number of moles of ethanoic acid and the number of moles of sodium ethanoate in the solution after the addition. Yep, that's the next thing that I would do. Then we're going to sub back in to our rearranged Ka expression to get a new H+, and then we'll be able to get the pH. It doesn't tell us what the pH of this one was before, so we can't compare the sort of before and after. Some questions you will, and that's where if you get a wildly different pH, you know you've probably done something wrong. So when it comes to this equilibrium that we're doing in part B, we've got ethanoic acid and sodium ethanoate. So ethanoic acid, CH3COOH, slightly dissociating into H+ and CH3COO-. And again, we are adding to our equilibrium mixture H+ ions. Now I want to know how many moles of those we're adding, which is fairly easy for me to work out because concentration is 1 and the volume is 10, which is 0.01 decimetre cubed. So the moles will be, that we're adding, 0.01. Now again, in terms of our equilibrium mixture, Le Chatelier said it will always act to oppose or counteract the change. So again, me adding a small amount of acid to this buffer is going to cause the position of equilibrium to shift to the left. And that means that we are going to lose some of our ethanoate ions, or lose some of the ethanoate ions, because it's those that are going to react with the H+ to make more of the weak acid. Now, because these exist in a 1:1:1 ratio, if I'm adding 0.01 moles of H+, I'm going to be losing 0.01 moles of CH3COOH and making 0.01 moles of weak acid, the ethanoic acid. So now we can think about what that's done to the number of moles that were in the solution initially. So, move that out of the way. Initially, in terms of the ethanoic acid, it said the concentration was 0.15, but because the volume is 1 decimetre cubed, we initially had just 0.15 moles of CH3COOH, and we've now gained 0.01 moles, so that's what we need to now add to the amount of moles, sorry, that we originally had. So now we have 0.16 moles of ethanoic acid. Same thing, but with the salt, we initially had a concentration of 0.1, but again, volume is a decimeter, so therefore the moles same as the concentration, and that would be the moles of the CH3COO minus, and then when we added the acid we lost 0.01 moles of the ethanoate ions because they reacted with the H+ ions, so now we only have 0.09 moles of the ethanoate ions. It is these new values for the moles that we're going to put into our Ka expression, obviously not that one because that's for the other question, but we would start by writing out a new Ka expression. So H plus CH3COO minus divided by the weak acid concentration. And it should always be concentrations when we write our Ka expression, but if you've watched my videos before, you will know that when I then rearrange the Ka expression to get the concentration of H+, that I'm going to be using the moles of these. I'm not going to be changing those moles into concentrations because the concentration and the moles will give us the same answer, because concentration is worked out by doing moles divided by volume. So if I do the moles of this, well, it would be, sorry, the moles of the acid. Let me just write that out first. Apologies everyone, I should have done that first. So if I use the moles of the ethanoic acid as 0.16 and divide it by the volume, and then I use the moles of the ethanoate ions, 0.09 divided by the volumes on the bottom are going to cancel. So it really doesn't matter if we use moles or concentrations here, and we have moles. I would argue don't make life harder for yourself by then having to convert back to concentrations. Now I therefore don't put square brackets in this step because I'm not going to use concentrations, and that's what square brackets mean. So Ka value 1.74 times 10 to the minus 5 times by the moles of the weak acid, which is now 0.16, and then we're going to divide that by the moles of the salt, which is 0.09, and that will give me my H+ concentration, and from there I can get pH. So 3.09 times 10 to the minus 5, and that's the H+ concentration, and then pH is equal to minus log base 10 of the H+ concentration, which is equal to, always 2 decimal places for pH even if they don't say that, so 4.51 to 2 dP. Now like I say, we don't have the original pH before the hydrochloric acid was added. Now I could work that out very easily actually, because all I would need to do would be to go back on my calculator and change the moles of the salt back to what they would have been, so 0.1, change the moles of the weak acid to what they would have been, so 0.15, that does give us quite a big difference in pH. And that is because, and I did think this when they gave us the information about the hydrochloric acid, that giving us 10 centimetres cubed of a 1 mole per decimetre cubed solution of hydrochloric acid, that's quite a lot of acid. Whereas a buffer is supposed to maintain an almost constant pH in the face of a small amount of acid being added. So here it says a small amount, and I would argue that is not a small amount. And in the modern day questions, they won't give you or you won't end up with quite as many moles. It would probably be something like 0.005, and therefore you wouldn't see such a big change in pH. But the concentration of the H plus ions has changed quite significantly, and thus the pH has actually changed by 0.07 pH units, which is quite a lot. So it will only maintain its pH when a small amount of acid or alkali or water are added, and that just goes to show why, I suppose. But yeah, hopefully that all makes sense. Let me know if it doesn't and there's anything I need to clarify, or let me know if you would like me to do another buffer question, a specific one or any of my choice, or any other types of questions. And once again, thank you so much for watching, guys. I hope you have a lovely, balanced, productive and restful weekend. Take care of yourselves. Catch you soon.